Okay, I've got a question anyway. So you have the new chiral metamaterial structure, which has these additional bars now.
Yeah.
And how does it compare to the previous one in terms of anisotropy? Is it more isotropic actually than the previous one?
No, it's more anisotropic. I didn't mention this. The original one had cubic symmetry, whereas the new one has tetragonal symmetry. Perhaps I can share my screen again and show this to you. I didn't emphasize this. You can directly see it from the unit cell here. If I go into the presentation mode, you have these connection arms in the XY plane, but you do not have them in the Z direction. So that
so it's really anisotropic.
So we directly staple the cells along the Z direction, but we loosely connect them in the XY plane. So it has a low symmetry.
Yeah, so effectively it's extremely anisotropic then. With okay.
Absolutely. I have said many times that it's uniaxial. Actually, that is not correct. It's tetragonal. That's the best I can say.
Okay, so effectively, I did not catch the fact that your bars are not along the vertical axis as well. Okay.
Yeah, this is a design part that we needed. For some time, I was under the impression that this was necessary to get this behavior that we first get an increase and then a decrease. But from Ehring micropolar elasticity, it looks as if it should also be possible to construct cubic symmetry crystals that have the same properties, but we have not found any yet.
Very interesting. Really, anyone is welcome to ask even the most naive questions. I'm sure that Martin would be more than welcome to enlighten us.
I saw Younes have a question.
Yeah.
You raise the hand.
Thank you, Professor. Hello, everyone. Thank you, Professor Wegener, for this beautiful presentation, and the organizers. Can you please go back to the dispersion curves of the chiral modes?
Yes.
Please.
You mean this image here?
Yeah, this one. Yes. So band structures are based on the unit cell technique by applying the Bloch boundary condition, right?
Yes. So let me be a bit more precise. We use Bloch periodic boundary conditions along the Z direction, but we use open or traction-free boundary conditions, of course, on the sides here.
Okay.
It's a finite beam in the XY plane, but it's infinite in the Z direction in this calculation.
Okay. So what makes you please say that this or that mode is hiding a chiral mechanism? I mean, if you refer only on the band diagrams, or you are verifying as well the mode, I mean the cartography.
Yes, very good question. From this band structure, nobody can tell whether the modes are chiral or not. Okay. That's why I showed you this example, and I'm going to show it again. I'm taking this one because it looks pretty much like all the others do. This is how the mode looks in space and time. And that's why I'm saying it's a chiral phonon.
Okay, okay.
And to be precise,
because a beam can...
Sorry?
Because a beam can give us exactly the same dispersion curves as ny, nx equal to 1 for a normal beam, I mean. And a plate, we will have the same as the second one and the third one, the same thing.
Yes, you're absolutely right. Except that here, due to the cubic symmetry, these two bands are degenerate. These are two bands. The
Yeah.
red curve down here
Yeah.
are two bands, and they correspond to the two orthogonal linear polarizations. These are the TA phonons, if you look at the modes. So this is what I would call chiral phonons. It's also interesting to look at the modes of these bands here, of the black and of the blue band. They are different. Without chirality, this would be the longitudinal band here, the pressure wave, so to speak, and the black one would be the ordinary twist mode that you also get in achiral architectures. If you now have a chiral medium, I'm telling you, but this is only something you can see from looking at the mode, you no longer have pure pressure modes and pure twist modes, but these two bands are getting mixed. You get mixed pressure twist modes. This is a bit difficult to visualize, so it doesn't only go like this. If you look at my image here, this would be a pressure mode. The twist mode would do this here, very roughly speaking, and now it's a hybrid of that. It's part of a helix. These phonons move as part of a helix. And the mixing between pressure and twist is different for these two bands. So actually one shouldn't really call this a twist mode. It's a mixed mode between pressure and twist. And this mixing is exactly the dynamic counterpart of the static experiments I showed you in the first part of my talk. There we push this like a pressure wave, and it leads to a twist, leads to a coupling. And here you get the same thing in the dynamic regime. And if you care about the details, if you look into this in Ehringen micropolar elasticity, it turns out that these two bands are coupled. Actually, I should say these two, but you don't see two down here. They get coupled. These two get coupled, but this one does not get coupled to this one. So they are kind of living in orthogonal subspaces for the symmetry that I have discussed.
In the experimental samples, you are performing these samples using nanoscribes?
Yes, these have been made by nanoscribe instrumentation. It's actually a fairly tall sample. A part has been left away here. The referee didn't like that. So in the paper, actually, you see the full structure. It looks very, very long, hardly fits on this view graph here. Yes, this has been made by a nanoscribe instrument. We have not performed wave propagation experiments on these very large samples yet.
So this is a very fancy dispositive.
Sorry, it's a very fancy what?
I mean, it's very expensive. I mean, can you, for example, predict that in 10 years or 20 years by now, can we use mechanical metamaterials in our everyday lives?
Well, this brings us back to this view graph here. Maybe I show it again. These large samples I showed in the first part are made with 10 to the 7 voxels per second. I did not tell you how long it took us to make this sample with the 300 billion voxels. It took us about 2 days. Meanwhile, we've gotten a little bit faster. It takes 1.5 days. So this is still not fast enough, I would say, to bring this into any application, really. To bring it there, we have to go in this direction here by another 2-3 orders of magnitude, I would say. Our applications will never come into reach, but that's something we are working on. In particular, Vincent Hahn, who I think is in the audience, is working on some pretty new approach by which we hope to get quite a bit up there. But this remains to be seen. But once again, this is the fastest 3D printing in terms of voxels per second that is out there at the moment on any size scale.
Okay, thank you, Professor.
And I've got a naive question. What is the finer resolution you can print? Can you print at the atomistic scale?
Well, I cannot, Sebastian. What we claim or what we report is shown in this figure here. So these points here mean that the feature size is a little bit below 400 nanometers or so. It's a fairly conservative number here. Actually, it's the average, if you want to be precise, between the lateral and the axial direction. if you look at other approaches, like step-assisted approaches or electron beam-induced deposition, they are better. Here you get down to about 100 nanometers feature size, but at the price of being 1, 2, 3, 4, 5, 6, 7 orders of magnitude slower.
And with your kind of techniques, you just want to speed up the printing process, or do you want also to reach finer resolution with the same kind of apparatus?
Actually, we want both. As you may know, we have worked our asses off for many years to go to the right here in this diagram to get finer features. Getting this together with increased speed is very, very hard, I would say. You can say that our best STED results are 1, 2, 3, 4 orders of magnitude slower than what we can do without STED. And I see no way out of this for the moment. I would love to go to finer features and higher speeds, but at the moment, I do not know how to do this.
And so with your current resolution, let's say about half micrometer, what kind of applications do you envisage? If you can really speed up the process by a few orders of magnitude, what would be the application, like, you know, Younes mentioned? I mean, what do we have in our daily life in, say, in 10 years? What would you envision?
Yeah, I mean, this now depends how broad you want to think. Let me think a bit broader here, not only mechanical metamaterials. These technologies are already going to industrial application today. Industry is buying these instruments to make micro-optical components that can be replicated. What counts there is not so much the feature size, but it's the surface roughness that you can get to. And that can be much smaller. You can go to 5 nanometer or below 5 nanometer surface roughness if you do it properly. And then you get optically smooth surfaces in micro-optical components. And that is already at the stage where fairly soon, I would think, you will hold in your hands components in your iPhone or whatever that have been made by two-photon lithography. There are other applications, for example, the making of scaffolds for biology, where one would like to be a bit faster, that it's really accepted in the biology community. And if you speak about metamaterials, I don't know. I think you really have to get 3 orders of magnitude, maybe more faster. Otherwise, you will have to charge somebody an arm and a leg for a little material that does something. I do not know. It depends. If you come up with a killer application, when it does something that you cannot do in any other way, perhaps people will accept that this will cost in the beginning 100 euros. I do not know.
Okay, so any more questions in the audience? You know, it's an opportunity to ask even. Yeah, please.
Hi, this is Stefan. First, thank you very much, Martin, for this high-quality presentation. I have just a naive question about not the performance of the printing, but the model seems like a small building with, for example, 12 story. What do you think about the extension of the application to another scale, at the scale of the building? Because very interesting to have this type of element. For the builder, it's easy to put all these elements to do something very high level construction, but maybe we can have the idea to reach very good, effective properties with the heat, maybe the earthquake and something like that.
Yeah, that's a very interesting idea. To be honest, I have not done anything in this direction, but you may know that there are 3D printers that print houses, and I mean really big houses in which people live. It's basically working by extruding concrete out of big nozzle and scanning that. For those people, it would be a piece of cake to 3D print architectures like that if there is a point. If you can come up with an architecture that is more resilient against an earthquake, for example, it can be done tomorrow, I would say. You just have to convince these people to 3D print it with their concrete 3D printer.
Stefan, could envision some kind of chiral bridge?
Of course.
A bridge with the structure of Martin's elastic metamaterial, but maybe this would, on the contrary, wobble.
Yeah. For a bridge, I think you
increase the wobbling. But
thank you, Martin. Thank you very much.
Sure.
There is also the idea, you know, of the, well, you know about this, about the cloak. So for an elastodynamic cloak, we need this kind of features to guide the wave.
Yeah, you're right, Sebastian. You know, we have discussed about this a number of times, but this is at least an order of magnitude more complex. At the moment, we have a hard time to map what we do onto continuum theory. What you would need for a cloak is the opposite direction. You would need a mapping from some wanted micropolar parameters to a microstructure. And I'm 100 miles away from being able to do that. I cannot hear you, Sebastian. It looks like you are saying something, but there's no audio.
My understanding is that you solved the direct problem, and now we need to solve the inverse problem. But you solved the direct problem.
Yes, you have to solve the inverse problem, but again, that's a lot harder.
Yeah, but essentially, you cannot solve the inverse problem if no one has solved the direct problem first, which you have done. So,
for particular examples, I make no claim that I have solved the forward problem in general. Yes, perhaps with some more experience in solving the forward problem, one can, by some intuitive approaches, solve the inverse problem. I'm just saying I am not able to do this at the moment, and I am far away from being able to do that.
Well, then nobody is. No, it's very interesting. And I have another naive question. So you mentioned that, so you're trying now to simplify the quasi-crystalline structure so that you could make it more amenable to fabrication.
Yes.
So this means that you want to reduce dramatically the number of connections without reducing too much the ordination. I mean, you have some kind of trade-off.
The general idea is the following. In a crystal, in general, you get very highly anisotropic behavior. However, it is not forbidden that in a crystal you get isotropic behavior. It's a very special case. In quantum mechanics, I would call this an accidental degeneracy. And at the moment, we are trying to come up with structures that do exactly that. They will have advantages and disadvantages. The advantage would be they look a lot simpler than what I've shown you so far. A lot simpler, really a lot. The disadvantage is they are going to be susceptible to details of the structure because it's an accidental degeneracy. You tune two bands to be similar that do not need to be similar by symmetry. That's the advantage in the quasi-crystal. That is totally robust to my understanding because there it's simply averaging over many different directions.
Okay. You see. Okay. So are there any more questions in the audience? Please.
Just curious. Who? Business. Just curiosity, Martin, how many joints, how many points, connection points do you have in your 3D rhombohedra unit cell?
I have to look it up again myself. Sorry.
Approximately, because it looks very close to an auxetic structure, and I think have also quite close property with auxetic structures generally.
Yeah, I know what you mean. Not sure about this. Oh, sorry. When you go to the view graph, actually I've scribbled the number of elements here. So for the 5.3 approximate, that's the one that gave us pretty good isotropy. We had 2,240 points.
Wow.
And about 300,000 rods in one unit cell.
That's a lot.
Yes, it is a lot, and it's so much that I am reluctant to tell you that we will ever be able to make this. And that's why we are interested in simplifying this design a lot and going perhaps 2 or 3 orders of magnitude down in the number of rods required. But again, as I was explaining to Sebastian, there is a price you pay.
Okay.
And sorry, but I did not catch this. The price to pay would be that you have less flexibility in terms of the defect in fabrications?
Yes, it's not going to
Okay.
be as forgiving with respect
Yeah.
to the structural parameter, because
Okay.
it's not an averaging effect, it's a tuning effect. You tune two
Yeah.
things to be similar,
Yeah.
and as soon as some geometrical parameter is off, your tuning is going to be off and it's not going to work.
Okay.
Okay.
So shall we call this to a close, or are there any more questions? I mean, anyone is welcome to ask once again any even naive question. You know, this is a totally new subject in general. It started like what, 3 years ago? This chiral elastic metamaterials. So
Yeah, that's when we got into this. I was making, in the beginning, I was making this remark concerning nature. So, for example, we do not go beyond nature. You find chiral mechanical effects in bones, for example. Roderick Lakes has discussed this many years ago. If you look at human bone, it is a micropolar and it has chiral elements in it. It's a bit confusing. It's racemic overall, because you will find left-handed and right-handed parts of some structural element in your bone, and it's there to somehow make the bone more stable. It's also used in crazy architectures of some beagles that use kind of a hammer to open things, and it's supposed to make the hammer that the animal uses more robust against cracks. And that also has chiral elements to it. So nature has looked into architectures like that long before us.
And you mentioned at the beginning that you were very reluctant to call a metamaterial something which is not rationally designed. But some people claim that actually metamaterials are structures which are not susceptible to disorder because they are based on local resonances. What do you make of this? Cannot you imagine that also metamaterial might be defined by its locally resonant low-frequency stop bands, so in the dynamic regime?
Well, yes, this is a definition that some people use, but you will have a hard time to apply this definition to the static case, because there is no resonance in the static case. That's why I do not find it so useful, because to me, the static case is one important part out of the general possibilities in metamaterials.
So essentially, effectively, that's right. Their definition would only work in the fully dynamic regime. Okay. Okay, so do we have any more questions? Anyone is raising his or her hand?
Meul raise a hand.
Yeah, sure. Please, Meul, go ahead.
Hi. I enjoyed the talk. It was really nice and well explained. I'm just wondering, so in terms of the quasi-crystal, is there any way to utilize, for example, Conway's theorem to simplify your design? So essentially for every finite partition of the region that you had of, say, characteristic length L, it would admit another one of an order 2L away. And this way you'd have some kind of mesoscopic homogeneity.
That sounds very interesting. I have never heard about this theorem, to be honest. That's something we should perhaps discuss. It would be highly interesting to simplify this architecture. That has been very difficult for us in the past. If there's any new avenue, very interesting.
Sure. I mean, in terms of that, I guess you're already using an approximation for a quasi-crystal to begin with. And this, in effect, would be another, it may already be wrapped up in the approximate. I have a fairly naive understanding of quasi-crystals. But in terms of this theorem, I take a patch. So if I took a patch, for example, in the Penrose tiling, the larger the patch is, the longer the distance is between that and the same patch that you see elsewhere. So you do end up with some properties of periodicity, although what happens in between these patches is ultimately pseudo-random. But the smaller the patch, the smaller the distance between them. So perhaps you could come up with some kind of effective medium theory that joins up these patches, and then you're converging to something that's a bit more tractable, I guess, and perhaps even experimentally buildable. It's just...
Yeah, right. But that sounds to me a lot like the approximants we are already using.
Sure.
Loosely speaking, the idea of the approximant is you take this complex quasi-crystal, you cut a small piece out of it, you wiggle it around a little bit that you can make something periodic out of it.
Sure. Sure. Maybe it's wired into that. I'm not familiar enough to say. But maybe it may afford another avenue. Once again, it's just an idea.
Yeah, thanks.
So, any more questions? I mean, the whole point of the webinar is that we interact. So if anyone has any questions, even philosophical one, this person is really welcome to ask his or her question. Okay, silence on the line. Let us thank our speaker again for this really wonderful talk. It was such an inspirational talk. I mean, fantastic.
Thank you very much, Sebastian. It has been my pleasure.
So our next webinar speaker will be Professor Andrea Alou from New York State University. Same day, same time. So we hope to see you again in a week. And please, also, you can let people have the link of Martin's talk. It will be made available permanently on the association website. So feel free to disseminate the link. Okay, thank you very much to everyone for attending, and hopefully see you next week.
Thanks, Sebastian. Thanks, Martin, again.
Yeah, thank you.
Thanks, everyone, for attending.
Bye-bye.
See you next week. Bye-bye.